so we're going to talk about problem number 2. For 2a, we want to identify the optimal solution from the set of equations. And this is our original problem, and this is the set of equations they're referring to. Now, this is the final set of equations, which corresponds to the final tableau if we were to use the simplex method to solve this linear programming problem. So after plotting our first row, the objective function row, and also our 2 rows representing our 2 basic variables, we see that this basically gives us the answer to our primal problem, as this is the final tableau. So for x1, we can read directly across the tableau like this, and we see that x1 is equal to 5/3. And we can read x3 directly across like this, and we see that x3 is equal to 3. Now the other variables are all set to equal to 0. So this is our final optimal solution for this linear programming problem. And plugging that back into the objective function for z optimal, we get that z optimal is equal to 17. For part B, we want to construct the dual problem. Now I want to leave the primal problem up here while we construct the dual problem because it's convenient to know the coefficients and some of the values from the primal problem. So first I wrote out this matrix containing the constraints from the primal problem, just so that later it's easier for me to read the transposed matrix from this original matrix. But we remember that we want to transform our maximization problem into a minimization problem. Specifically, we want to minimize W, and we get the 25 and the 20 from the B vector of the original primal problem. So we want to minimize W such that these constraints apply for Y1 and Y2. Now, where am I getting these coefficients? I'm getting them from the transposed version of this matrix. So 6, 3 corresponds to 6, 3, 3, 4, 3, 4, 5, 5, and 5, 5. Now the 3, 1, and 4 are from the original primal problem's objective function coefficients, and that's where you get those. And of course, don't forget to add on the greater than or equal to 0 constraint for all of your y variables. And that is our dual problem. Okay, so now part C wants us to identify the optimal solution for the dual problem from the final set of equations. Part C, yes, okay. So for part C, we want to first map the original primal variables to the new dual variables. So by doing this, we want to map the primal slack variables to the dual main variables and the primal main variables to the dual slack variables. Now, from complementary slackness, after mapping this, we know that any non-zero primal variables will map to 0 value dual variables, which is why from x1 and x3 being equal to 5/3 and 3, respectively, we know that y3 and y5 are actually both equal to 0. Now, using our dual formulation here and subtracting some slack variables, we arrive at our dual canonical formulation, which is right here. We have now converted our system of inequalities to a system of equalities, and given the fact that we know that y3 and y5 are equal to 0, we can solve for the rest of the variables. And let's go down to look at those values. So this is solving the system of equations, it's just showing the work, and we find that y1 is equal to 0.2, y2 is equal to 0.6, and y4 is equal to 2. Now we want to focus on y1 and y2 here, since they're the actual main variables in the dual problem. Now we plug them into to minimize the W objective variable, and we find that W becomes 17. And by complementary slackness and duality theory, actually, we know that this shows this is indeed the optimal solution, since it is equal to the primal optimal solution. And again, verifying this graphically, so here I've plotted these 3 lines are the dual constraints, and this purple line is actually the dual objective function isocline. So we see that this isocline actually overlaps the feasible region of the dual problem exactly right here at this point, 0.2, 0.6, which corresponds to our solution right here. So we know, now we've also verified graphically that this is indeed the optimal solution for the dual problem. Now I want to take you guys on to 2D, which asks us to use duality theory to determine whether a changed version of the original problem can still take on the original optimal solution and have those optimal solutions remain optimal. So to evaluate whether or not the original optimal solutions still hold for the new problem, we want to construct, again, the dual formulation. And we notice that the x2 variables have been changed throughout, so in the objective function and also in the constraints. Knowing that, we notice that we have a completely different constraint right here in the dual problem, since this column in the primal problem corresponds to this constraint in the dual problem. Now we run through these inequalities, or rather constraints we need to have our optimal solution satisfy, and we plug in the original optimal solution for the dual problem, 0.2 and 0.6, and see whether or not it works out for all of these inequalities. And it makes sense that it does not work out for the second constraint, since it comes from the changed coefficients of the second variable in the primal problem. Actually, when you plug it in, this side comes out to be 2.2, which is not actually greater than or equal to 3, which means that the solution is not optimal as it violates a constraint in the new problem. So therefore, we can conclude that the solution is not optimal. Now for 2e. So 2e wants us to use a fundamental insight to find the new coefficients of x2 in the final set of equations after it has been adjusted for changes in the previous problem. So this is coming from this problem right here. So we're going to use a fundamental insight. And the fundamental insight basically tells us that we can manipulate some of the original matrices that were given and that we can derive from the original problem to find the final matrix of the problem without having to solve through the entire set of tableaus. And we do that by this. We find that xb is equal to b inverse times b. Now this b is just, actually, sorry, I want to focus on this line. So xb is actually b inverse times matrix A, and that would be the coefficient of the original variables for xb, which are our basic variables. Therefore, for x2, we apply this formula right here, b inverse, which we've derived and is right here, and A. Now, I know you're probably thinking A has a lot of different vectors or a lot of different columns, so why is it just a 2 by 1? Now we're actually picking out just the coefficients for x2 since that's our variable of interest. So we would just take that from the constraint, and that's just 2 and 3. So after multiplying these two matrices out, we get that the new coefficients for x2 are negative 1/3 and 4/5 in the final set of equations for the new adjusted problem. Okay, so for 2x, now we've actually added on the new variable to the new problem, to the original problem. And now we want to use duality theory again to determine whether the previous optimal solution along with x is equal to 0 is still optimal. So we do the same thing that we did in part D, and we plug in the original solution. Well, first we construct the dual, and now you see since there's a new x variable, a new primal variable, we also have an additional dual constraint since complementary slackness maps that. And plugging in the original optimal solution, 0.5, 0.2, and 0.6, we see that this new solution is this original solution actually violates this particular final constraint in the dual problem. And that makes sense since this final constraint was added on after we added on the new primal variable. So again, the left side comes out to not be greater than or equal to 2, which violates this constraint, which means that the original solution is not optimal for this new adjusted problem. And finally, for part 2G, we're almost there. It wants us to use the fundamental insight again to find the coefficients of x and u in the final set of equations. And we use the same thing we used before. xb is equal to b inverse times a. Now this is our b inverse as from before. And now this a is from the coefficients of x and u in our problem that we were presented with in the previous part. So after multiplying out these two matrices, we find that the new coefficients for x and u are 1/3 and 1/5. And that's it for problem number 2. Let's do problem number 3. So number 3 is classic resource allocation problem using dynamic programming. Here, the resources are the number of days we have to study. And the groups that we're allocating these resources to is our courses that we have, 1, 2, 3, 4 different courses. So now the courses define the stages, which are, again, are the groups that we allocate the resources to. And the states are defined as the number of study days or resources remaining to be allocated to these courses or groups. And I want to define our decision variable before I touch on this variable here, which is a little bit more different in this problem compared to other dynamic programming problems. Xn is our decision variable, and we're using it to represent the number of days allocated to a particular stage or course in this case. And therefore, attached or associated with xn is the variable pxn, which I define as the number of points associated to when xn days are allocated to stage n. Okay, so now we can get started since we've defined, actually before we do that, I do want to touch on our mathematical formulation where we plug all of these variables in, and this is the equation we're going to be referring to when we run through all of these tables later. So we're defining the optimal objectives at any stage as the maximum, because of course we want to maximize our point values in how much we study for these courses. So the max xn definitely has to be greater than or equal to 1 because that was defined in our problem because we have to study for every course at least 1 day, and that's where the 1 comes from. And then Sn is the upper bound at each stage for xn. So we take the point value associated when xn days are allocated to stage n, and then we add on top of that the next stage's optimal value, and we use Sn minus xn in here to be equal to Sn plus 1 because Sn minus Xn gives us exactly how many resources or days we have left over to allocate at stage n plus 1. And we're going to touch on that later, and this is going to make a lot more sense when we actually plug numbers in for each stage. So let's start at stage 4. Because this is a dynamic programming problem, we want to work backwards because everything we do in these stages is, so for example, what I decide on for stage 4 depends on what I decide on for stage 3. So stage 4 is the easiest to start at because we want to start here and then start working backwards due to the nature of this being a dynamic programming problem. So let's look at S4. We know that we have to have at least 1 day left when we get to stage 4, which is our last course that we're studying for. So course 4, the minimum of S4 is 1 and the maximum is 4 because our total constraint is 7 days. So if at the very least we use 1 day to study for each of the other 3 courses, we would still have 4 days left over for the last course, course 4. And then 4, 4, 5, 8 here is actually corresponding to this column here in our estimated grade points table. And each of these is associated with studying for 1 day for course 4, 2 days for course 4, 3 and 4 days for course 4. And that's how we are getting this column. So stage 4, pretty simple. Let's move on to stage 3. So here we have to start doing some additions. Well, first let's define our lower and upper bound for S3. The lower bound on S3, we have to have at least 1 day left for S3 and 1 day left for S4. So by the time we get to S3, the minimum number of days we should have before we allocate anything should be 2. And then of course the upper bound is 5. So let's run through one column and hopefully these should all start to make sense. So if by the time we get to studying for course 3, we have 2 days left and we allocate one of these days, we should be looking for, if we, first of all, the point values of allocating 1 day to study for course 3. Let's look at this table. 1 day for course 3, that's 4, and that's where this first 4 comes from. Now, this 4 comes from up here. Because think about this, looking at this equation, we still have to account for what happens at the next stage, which is stage 4. And if we use 1 on stage 3, we will have 1 more day left for stage 4. And that would be S4 is equal to 1, which is 4. So 4 plus 4 is equal to 8. And let's run all the way down here to hit the other extreme and get a better idea of what I'm talking about. So for example, if you have 5 days left when you get to stage 3, and you decide to allocate 1 day to stage 3, you would still have this 4, which you get from this table right here, as we did before. However, for this part of our objective, our optimal objective function, you would actually have 5 minus 1, which is equal to 4 days left for stage 4. And which is why we take this 8, because that's the value associated with spending 4 days on course 4. So 4 plus 8 is equal to 12. And all of these other columns kind of work the same way. You would just take this first value here from this table and trace whether you're studying 1, 2, 3, or 4 days for this particular course. And then you would add on top of that, the second value would be the value from your previous, or rather your next stages table. And then we do this. Notice these ones are hashed out because we really can't calculate these. For example, you have 2 days left on S3. You can't really afford to give 2 days to S3 because remember our constraint that we need to spend at least 1 day studying for every course. And that's why these are hashed out, because they just don't work according to our constraint and they don't fit in. And we get these optimal values. Now, we know this pretty well by now, so we can really fly through the rest of this. You do the exact same process for n is equal to 2, except now your first value, you're referring to the course 2 column in this grade point table. And then for your second value, you're referring to n is equal to 3 table, actually, in particular this column. And then we hash values out again because they're simply not feasible. And then we get these values. Now notice at stage 2 is where we start to get some of these multiple solutions. For example, whether you study 1, 2, or 3 days for course 2, you get the same number of grade points if you came in with 5 days left over, which is why you have 3 solutions here. And then for 6 days, you have 2 solutions over here. Now let's look at n is equal to 1, stage 1. So this is our first day. This one's interesting because we have to cap our S1 at 7 exactly. Because think about it, when you're starting to study for these exams, on day 1, you have exactly 7 days to study no matter what. So you don't really have an upper or lower bound for your S. And we use the same method we used before, refer to this column to table, and the previous or the next stages table. And then we get these values. So here, it's very interesting. We have our optimal number of grade points that we can gain from studying effectively like this is 21. And we see that this comes from actually whether you spend 3 or 4 days studying for course 1. So we're going to have 2 different optimal solutions. The first optimal solution is x1 is equal to 1, x2 is equal, x1 is equal to 3, x2 is equal to 1, x3 is equal to 2, and x4 is equal to 1. The second optimal solution is 4, 1, 1, 1. So you see, even though these two different solutions are different, because we work backwards, we're able to capture the two different routes we can take to get at the same maximized grade point, which is 21 points. And that's the magic of dynamic programming. Number 4. Problem number 4 asks us to use branch and bound to solve this mixed integer programming problem. Before we start, I just want to point out that mixed integer programming refers to the fact that here, x4 out of x1 through 4 actually does not have an integer constraint. And that's going to come up later in our optimal solution, and I will point it out again later in our solution. So we first start by using LP relaxation to find a relaxed optimal solution with the simplex method. So by ignoring this final constraint saying that x1 through 3 have to be integers, we can just use a simplex method to solve this problem. And I plug this into Excel to solve the simplex of the LP relaxation. And then I get this relaxed solution. Now this doesn't look very pretty. Obviously, the variables that need to be integers are not integers, but it's a great starting point. So let's make this our first node. Next, to start the first iteration of our branch and bound algorithm, we have to choose a branching variable. Now the branching variable is arbitrary, you can pick whichever one, but rule of thumb is to pick the first one you see that is supposed to have an integer constraint that is not an integer yet, which in this case, it is x1. So our subproblems 1 and 2 are going to come from this value. Now 32 over 15, that is 2.5, it's 2.2 something. And now we're going to take the floor and the ceiling of that, and we're going to search on both sides, meaning we're going to take the ceiling, which is 3, and we're going to search anything greater than or equal to 3. And then we're going to take also the floor, which is 2, and search anything less than or equal to 2. Now the great thing about an integer problem is that x1 is constrained to be an integer. Therefore, we know that there's no actual space between 2 and 3 in which x1 can exist. So we know x1 has to be greater than or equal to 2 or less than or equal to, has to be greater than or equal to 3 or less than or equal to 2. So subproblem 1 is our original problem plus this constraint. And then subproblem 2 is our original problem plus this floor constraint. Now let's look at our solution for subproblem number 1. We get x optimal is equal to 3, 0, 21 over 4, and 1/4, and this z value. And for subproblem number 2, we get this solution. And neither of these have integer values as well. And now I want to bring into focus our fathoming test that we use to evaluate whether or not our solution is truly optimal, or maybe it's fathomed. And we're going to apply each of these fathoming tests to every single node. So fathoming test number 1 is that its bound is less than or equal to, for a maximization problem, that the bound is less than or equal to the current incumbent, or the current optimal z value. In this case, it doesn't really apply because we don't have a current incumbent quite yet, so we're going to look at 2 and 3. 2 says its LP relaxation has no feasible solutions. These two both have feasible solutions. And 3, the optimal solution for its LP relaxation is integer. They're not integer yet, so by all these fathoming tests, these two nodes are not fathomed yet. Therefore, we have to branch both of them in our future iterations, which we're going to do right now. Node 2 branches into subproblems 3 and 4. We're going to pick the branch variable for node 2, and the first one I see going down the list that's not an integer that should be is x3. And x3 is equal to 5.25 right now, so we're going to branch it into the original problem plus whatever constraint already exists, which is x1 is greater than or equal to 3, right here and right here. And then the two branches are going to be x3 is greater than or equal to the ceiling, which is 6, and then x3 is less than or equal to the floor, which is 5. And that's just what we get from rounding 5.25 up and down. So by running these through the fathoming test again, we see that subproblem number 3 actually has no feasible solution, or no optimal solution. Therefore, it's fathomed by test number 2. Subproblem number 4 has this solution. We run it through all the tests. We realize that it actually does have optimal solution for its LP relaxation, and in which the variables that need to be integers are integers. So we realize that this becomes our current incumbent, and it's fathomed by test number 3. So this is our running incumbent right now, and we're going to branch node 3 now into subproblems 5 and 6. Now node 3, I'm also going to pick x3 as a branch variable, which right now is 3.57. So I'm going to branch that into greater than or equal to 4 and less than or equal to 3. And again, we have to remember to carry over our original problem and any additional prior constraints. We find a solution for subproblem number 5 and subproblem number 6. Now let's run these by the fathom test again. I'm not going to screw up anymore because we know them by heart now. The optimal solution for z for both of these is actually less than 195. And 195, remember, is our running incumbent that we have to run all of our nodes' optimal solutions by. So according to our fathoming test number 1, both of these nodes actually become fathom because they're not optimal compared to 195. But remember, this problem is about maximization. And if your optimal solution isn't greater than the current optimal solution, then we don't need to explore those nodes any further. So now we revisit some of the nodes that we haven't fathomed before. And actually, I'm going to scroll down to this very succinct branch and bound algorithm chart that I've drawn. So it's this tree. And we see that F3 is our current incumbent and Z is equal to 185 is right here. So we revisit node 2 and node 3. And we actually see that node 2 and node 3's optimals are both less than 185, so they're actually both fathomed by test number 1. Now all of our nodes have officially been completely fathomed. There are no unfathomed nodes remaining. So we know by the branch and bound algorithm that node 5, our running incumbent, is indeed the optimal solution. And that is it right here. And if you look at my lab report, I also provide more explanation right here as to why all of the other nodes are fathomed by each of the fathoming tests. So now we are going to solve for problem number 6. Part A asks us to use the KKT conditions to solve for the problem's optimal solution. So KKT conditions, there are 6 total, but because there are 2 variables here, we have to repeat parts 1 and 2 for each of the variables. And then, so we can see here, it's 2 minus x1. So this is the derivative of the x1 terms, and then this is the derivative of the x2 terms. So we take the derivative minus mu, set that less than or equal to 0. And then number 2 is you multiply that by the original variable and set that equal to 0. Part 3 is just the actual constraint itself. So actually parts 1 and 2 have to deal with the objective function. Part 3 is the constraint. Part 4 multiplies a modified version of the constraint by mu, setting that equal to 0. So now we have 1, 2, and 3 different equalities to work with here. And then 5 and 6 are again just greater than or equal to 0 conditions for all of our variables, including mu, which we introduced. So after graphing this, we notice that all of these variables actually lay on the outside boundary as far as the optimal solution goes. So we know for sure that none of these values are going to be equal to 0. So now we dive into our KT condition equalities and we try to solve. So first I set it up as I use number 4 to get x1 in terms of x2. Then I use 2a and 2b, and I set these expressions in parentheses equal to 0, and I solve for x1 in terms of mu, and then x2 in terms of mu. And after doing this, you can use this expression that we got from number 4 to actually solve for mu, because now you can represent both of these variables, x1 and x2, in terms of mu. So solving it, down here we see that we found mu is equal to 0.5. And now solving for x1 and x2 is fairly easy. You plug mu in. x1 is 0.75, and then x2, plugging mu in, is 1.25. We see that all these values satisfy all the KKT conditions listed up here, all 8 of them, and therefore we know that this is indeed our optimal solution, which is that x is equal to 0.75 and 1.25, and then mu is equal to 0.5. B asks us to formulate the modified simplex method. So here, to modify the simplex method, to use the revised simplex method, we turn this into a minimization problem, and we have these new variables, mu, y1, z1, and then y2, z2, and then also z down here. And this is just these variables are just to turn the original problem into equalities, which is why we need these additional variables. And then with these additional variables also come this complementarity constraint, which is stated right here. And then we're going to tackle all of this in a later section, so I'm going to expand more on what these mean later. For part C, it wants us to confirm that our answer for part A is indeed an optimal solution using our formulation of the modified simplex method in part B. So that's what we're going to do. We're going to take 0.75, 1.25, mu is equal to 0.5, and we're going to plug them in. Mu is the same thing as u here, by the way. We're going to plug them in into these equalities we have, which are really easy to work with because we've used these additional variables and constraints to get them down to equalities. Plugging these in, we don't have z1, y1, or z2, y2 yet, but after plugging some of these value into x1 plus x2 plus v is equal to 2, we can solve for v, which is actually 0. So then we plug v is equal to 0 into the complementarity constraint, which is the additional constraint, and that's actually going to help us solve for y1 and y2, because we see that for them to be equal to 0, and given the fact that they both have to be positive, y1, y2 have to be both equal to 0. Therefore, we plug y1, y2 into these two equations, 1 and 2 here, and then we see that z1 and z2 both have to be 0 as well. So now we see that the optimal solution is indeed at x is equal to 0.75 and 1.25 because all of these additional variables have come out to be 0. So if you plug it in, x is 0.75 and x1 is 0.75 and then x2 is 1.25. Okay, part B asks us to apply the modified simplex method, so that's an extension of part B of the problem. So here I've actually simplified it a little bit more. I've replaced some of the funkier variables I used up there with just additional x variables, and then some more adding flex variables to make these constraint equalities. And then I actually have an attached tableau here. Give me 1 second to pull it up. Okay, so here's the tableau that I got from Excel. I just punched this first table into Excel and I started working on it using row operations to get the necessary rows into reduced row echelon form, and then figuring out what my entering and leaving basic variable is. Basically, after 1 iteration, 2 iterations, we arrive at our 3rd iteration and we get our optimal solution. And we have again confirmed that it's 0.75 and 1.25 for optimal X solution. And this is just all done exactly how we did at the beginning of the semester. It's very simple. It's just really just row operations that I've done in Excel. Okay, so now we're going to jump back into this. Okay, so part E asks us to use dynamic programming to solve this problem. Now, this problem does have nonlinear objective function, which makes it a little bit tricky, but it's actually very simple once we know that it's separable. So first we work at stage 2, which is the variable x2. And we just take the part with the x2 terms out and we try to maximize that part alone. And we notice that x2 basically has to be equal to s2, whatever's left over by the time we get to stage 2 in order to be maximized. So we leave it at that. All of this is just random work I showed in the middle, but it's not important until right here where we dive into stage 1, because we've already found our maximization function for stage 2, which is 3s2 minus s2 squared. And we can plug that in here. That's our maximization function for stage 1, and that's our F1 optimal. So you plug that in as S2 into 2 minus X1. So you plug 2 minus X1 as S2 into this formula we have up here. And I show that work right here. So 3s minus 3s2 minus s2 squared becomes substituted in this way. And then we get this in terms of X1. So now we can plug this into the maximization formulation and then simplify it some more expansions. And then finally we get down to this equation, which is how we're going to maximize our F1 function. We test for concavity, so we take the first derivative, we take the second derivative. It's not very clear here, but it actually says -4. We found the second derivative as being negative, which means that the graph is concave. And this shows, knowing what concave graphs look like, we know that they are holding their maximum at the midpoint of this graph. Now we go back to our first derivative, set it equal to 0 to find the root at which this maximum occurs. And we find that x is equal to 3/4, or 0.75. And x2 is very simple to find from there. It's just 2 minus 0.75 because 2 is in our constraint. That's all the slack we have to give to x2. And then x2 optimal is 1.25. Solving for z optimal, we get z is equal to 3.125, given x1 and x2 optimal. And again, we've confirmed that this is our optimal solution. And finally, I just wanted to run you through part F, which is using Excel to solve this quadratic programming problem. So I actually used an add-in solver on Excel, and I just initialized the variables all as 0. I typed in my constraints, I typed in my objective function, and you go into solver. This is what it looks like. You select your objective cell, which is this cell, which is that cell, and then you select your changing variable cells, and then you also tell it which row is holding your constraint, which is this one. And then once you click solve, it turns out this other really nice little table. And as you can see here, the optimal solution for x is, again, indeed, 0.75 and 1.25. And our z optimal is also confirmed. It's 3.125. And that's all for problem 6. Thanks.